9.10 Lesson 4, Taylor and Maclaurin Series. Our objectives for today are to apply Taylor series to do problems like we see in our three objectives. The first objective is to find a power series representation for f of x is equal to sine squared x, or we'll take a look at that by first rewriting the function using a trigonometric identity. Because yesterday we learned the basic list of power series, or the list of power series for basic elementary functions. And one of them, of course, was sine. But here we don't have sine, we have sine squared x. So we'll see how we can do that. Objective 2, you'll be able to represent a function with a power series. And then you will use the power series representation of the function to find a limit of the function. We'll look at an example for that. These are applications of power series, how we use power series to do other math problems. Objective 3, you'll be able to approximate the value of a definite integral by representing the integrand with the power series and then applying the fundamental theorem of calculus. Remember, you can only apply the fundamental theorem of calculus if you are able to find an antiderivative of the integrand. Now, you may have a function for which you're not able to find an antiderivative, but if you represent that function with a power series, then a power series basically it has terms that are power functions, and therefore you can integrate a power function easily. So you'll see that as a part of today's lesson. Vocabulary, in Objective 3, we'll be looking at a definite integral. So, for example, you might have something like sine of x squared. That would be our integrand. This would be called a definite integral because it would have what we call limits of integration. And normally we use the fundamental theorem of calculus to evaluate a definite integral, but one requirement for you to be able to use the fundamental theorem of calculus is that you need to be able to find an antiderivative of the integrand. If you have sine of x squared, you're not able to find an antiderivative. So how would we go about approximating the value of this definite integral? We'll see that in Objective 3. So now we will begin with Objective 1, finding a power series representation for f of x is equal to sine squared x by first rewriting the function using a trig identity. Example 8, find the power series for f of x is equal to sine squared x. Now make sure you understand that the function is sine squared x, which means you actually have sine x times sine x. So how do we do this? Well, let's look at what we learned yesterday. So we have power series for elementary functions, and we know the intervals of convergence for each of these power series. We do have a power series centered at 0 for sine x, but we don't have sine x, we have sine squared x. And yesterday we saw operations with power series, such as doing composition. Although it is possible to multiply two power series together, and we'll see that tomorrow, if you can do it in a different way, it's better to do it avoiding multiplication. So you do have a product, and you have the power series for sine x, but maybe you don't necessarily just want to multiply, because how do you multiply two infinite series? Well, you have to use the distributive property. So you're going to be distributing each term to an infinite number of terms. So although it could be done for some products, it's not something that you want to do if there is another way you can do it. So what other way might we be able to represent sine squared x? We will remember something from trigonometry called a power-reducing formula. These power-reducing formulas are trigonometric identities. So using the power reducing formula for sine squared u, I'm able to rewrite my function f of x. So in other words, what is this? Sine squared u, whatever you have for u, you will have twice that when you rewrite using this power reducing formula. So for example, let's say you have sine squared of 5 theta. Then when you rewrite sine squared of 5 theta using this power reducing formula, you're going to have 1 minus cosine of 2 times 5 theta, which would be tan theta. That would be tan theta over 2. So in our case, we just have x. So we will have 1 minus cosine of 2 times x over 2. And of course, this is equivalent to sine squared x because we use the power reducing formula, which is a trig identity. So what can we do with 1 minus cosine 2x over 2? We can write it as 1 over 2 minus cosine of 2x over 2. 1/2 is just a constant, and then you have cosine of 2x over 2. Be careful of one thing. The 2x is what we call the argument of the cosine function. You're not multiplying cosine by 2x, you're taking cosine of 2x. And because of that, you cannot cancel the 2 in the denominator with the 2 in the argument. If you had 2 times cosine of x over 2, then you could cancel because you have multiplication, so you can cancel with the 2 in the denominator. But that's not what we have. So what we have to do is the following. We have to use the power series centered at 0 for cosine and replace x in the power series for cosine with 2x. And that would give us a power series for cosine of 2x. And then we would have to divide each term of that power series by 2. And then, of course, we have 1/2 minus that. So let's see how we do that. One thing that I can do is I can rewrite cosine of 2x divided by 2 as 1/2 times cosine of 2x. It's not important. If you prefer to do that, you can. 1/2 times cosine of 2x. And again, what are we going to do? We're just going to do the following. We're going to write f of x, and I'm going to write this 1/2 here, which is just a constant. So I'll write 1/2 minus, and then I have this 1/2, which is multiplying cosine of 2x. So this 1/2 is going to multiply the power series for cosine of 2x, which I will write in brackets here. And the power series for cosine of 2x, I can get that very easily by using the power series for cosine of x and replacing x with 2x. So I will have, the first term will be 1 minus, and then I will have 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial, and so on. And if you want to write the nth term, you can. The nth term will be negative 1 to the n, and I will have 2x to the 2n over 2n factorial, and of course you keep going after that. So that would be the power series for cosine of 2x. One thing that you can do is you can distribute this 1/2. because 1/2 is multiplying cosine of 2x, so 1/2 will multiply the power series representation for cosine of 2x. So you can distribute the 1/2 to each of the infinitely many terms in the power series for cosine of 2x. And when you do that, this is what you have. You have f of x is equal to, you have this 1/2, which is by itself, and then you're going to distribute the 1/2 that's multiplying cosine of 2x to the power series for cosine of 2x. So 1/2 times 1 is 1/2. So you have minus. Don't forget, it's actually minus 1/2. So let me just say you will distribute negative 1/2 to each term of the power series for cosine of 2x. Or you can think of it as subtracting 1/2 times each term of the power series for cosine of 2x. So you have minus 1/2, and then distribute negative 1/2 to the second term. Negative times negative is positive, and you will have 2x squared over 2 times 2 factorial. Distribute negative 1/2 to the next term, you have minus 2x to the fourth over 2 times 4 factorial. Distribute negative 1/2 to the next term, you have plus 2x to the sixth over 2 times 6 factorial, and so on. And that's what you'll have. And when you simplify, one thing that is nice is that at the very beginning, you have positive 1/2 minus 1/2. So they will add to 0, and you're just left with f of x is equal to 2x, the quantity 2x squared, divided by 2 times 2 factorial, minus the quantity 2x to the fourth power, divided by 2 times 4 factorial, plus the quantity 2x to the sixth power, divided by 2 times 6 factorial, and so on. So you can write a description of the nth term. You can write 2x. Let's say we make n equal to 1 for the first term. If we make n equal to 1 for the first term, then the exponent here, 2, would be 2n. 2 times 1 is 2. So I'll write 2n here over. It looks like one thing that's common about the denominators is you always have that factor of 2, which is coming from distributing the 1/2 to each term. So that's regardless of what term I'm looking at. And then you have 2 factorial, 4 factorial, 6 factorial. It matches the exponent that you have in the numerator. So you're going to write 2n factorial. And there's our power series that represents our original function, which is, of course, sine squared x. So here is the final answer for our problem. Our function is f of x is equal to sine squared x, which we were able to rewrite using a power reducing formula, a trig identity, as 1/2 minus 1/2 times cosine of 2x. And then we were able to use the power series for cosine of x and replace x with 2x to get the power series for cosine of 2x, which we then multiplied by 1/2 and subtracted from 1/2. So when we do that, this is what we have, and you can write it this way using sigma notation. You do need the negative 1 to the n plus 1 power to account for the alternation of signs. So going back to my previous screen, I do need to make an edit here because I forgot that. So you need to have negative 1 to the n plus 1 power to account for the alternation of signs. This series converges for all real numbers x, and if you'd like to verify that, you may do so by using the ratio test. So we just looked at objective 1. We found a power series representation for f of x is equal to sine squared x by first rewriting the function using a trig identity and then using the power series centered at 0 for cosine of x. Now we'll take a look at objective 2. You'll be able to represent a function with the power series. You will use the power series representation of the function to find a limit of the function. So we have 53 here. Use the series representation of the function f. And here's the function f. We want to represent this function with a power series. And then we want to use the series representation of the function f to find the limit of f of x as x approaches 0. Before we do that, I would like to remind you of something that you learned in the early part of Calculus AB. And if you remember that, you will instantly know what this limit is. But of course, we would like to follow the instructions and do the problem the way we're being instructed to do it. But I would like to, just for the sake of reminding you of something that you learned in Calculus AB, look at a theorem from Chapter 1. So as you can see from Theorem 1.9, the limit of 1 minus cosine x over x as x approaches 0 is equal to 0. And we will find that by doing it the way we're being asked to do it, using the series representation of the function f to find the same limit, and of course we'll get the same answer. You could even use L'Hopital's rule, and you will also get 0, so let's take a look at that as an alternative. If you want to find this limit using direct substitution, you would substitute 0 for x. We know cosine of 0 is 1, so in the numerator you'll have 1 minus 1, which is 0. And in the denominator, when you do direct substitution, you get 0. This is an indeterminate form for which you can use L'Hopital's rule, and therefore we will go ahead and do it that way. So in the numerator, the derivative of the function 1 minus cosine x would be the derivative of 1 is 0, so you have 0 minus the derivative of cosine x, which is negative sine x. 0 minus negative sine x is sine x. And in the denominator, the derivative of x is 1. The derivative of x with respect to x is 1. And when you take the derivative, okay, so we've done the derivatives. Now you have the limit as x goes to 0 of sine x, of sine of x. So you can do direct substitution, and sine of 0 is 0. So you get the same limit. And we're going to do it using power series today. Use the series representation of the function f to find the limit of f of x as x goes to 0, if it exists. It does exist, and it is equal to 0, and we'll get that using power series. So what we can do is we can use our Taylor series centered at 0 for the function cosine x, and we can go ahead and replace cosine x in the numerator of our function with the Taylor series centered at 0 for cosine x. And that would give us the following. In the numerator we'll have, there is a denominator, which is of course x, but in the numerator we're going to have 1, which is this 1 here, minus, in parentheses, you need parentheses because you need to distribute the minus sign to every term of the power series for cosine x. So what is the power series for cosine x? It's right here. So we write 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on. It just keeps going. You can write the description of the nth term if you'd like to. It turns out that it's not really needed for this problem, and you'll see that in a moment. So in the numerator, when you distribute the minus sign, you get the one that you had out front minus 1. 1 minus 1 is 0. So it simplifies, the numerator simplifies, and of course you still have to distribute the minus sign to the remaining terms of the power series for cosine x. So that will just change the sign of each term. So when you do that, you get x squared over 2 factorial. But then don't forget, you're dividing each term in the numerator by x in the denominator. And of course, you have to divide each term in the numerator by x. Dividing by x is the same as multiplying by the reciprocal of x, which is 1 over x. And what that will do is it will cancel with a factor of x that's in the numerator of each term. So basically, instead of having x squared over 2 factorial, I'll have x to the first power over 2 factorial. And then the remaining terms are going to be minus x to the third over 4 factorial plus x to the fifth over 6 factorial plus x to the seventh over 8 factorial, and so on. And let me just go ahead and use red ink here to sort of separate what was before it from what we have here. And of course, there are infinitely many terms. We have infinitely many terms in our series, so I'm going to use parentheses. I have this ellipsis to show that there are, in fact, terms that continue beyond the 4 that I wrote. But it doesn't really matter. And the reason why it doesn't really matter is because you're taking the limit of this infinite series, but all of the numerators have an x in them, raised to some power, either the first power, the third power, the fifth power, the seventh power, and so on. And you're taking the limit of this series with infinitely many terms as x goes to infinity. So how do you take the limit? Well, you're going to do direct substitution. And when you do direct substitution, you're going to substitute 0 for x wherever you see x. And you see x in the numerator of every single term from our infinite series. Therefore, every single term of our infinite series will go to 0, so the limit of the function is equal to 0 as we expected. So we just looked at objective 2, in which we represented a function with the power series, and then we used the power series representation of the function to find a limit of the function. And now we'll look at an example for objective 3. You'll be able to approximate the value of a definite integral by representing the integrand with the power series and then applying the fundamental theorem of calculus. So you might ask, why not just directly apply the fundamental theorem of calculus to begin with? Because the integrand of the original problem, you may not be able to find an antiderivative of that integrand. And if you can't find an antiderivative, you cannot use the fundamental theorem of calculus. But representing the integrand of your problem with a power series would allow you to find an antiderivative of the power series, because what you have is a power function for each of the terms from your power series, and you know how to integrate power functions. So we look at this problem for our third objective. Use a power series to approximate the definite integral of sine of x squared from 0 to 1 with accuracy to 4 places after the decimal. So again, the fundamental theorem of calculus states that if you are able to find an antiderivative of the integrand, you can evaluate the antiderivative at the upper and lower limits of integration and subtract, and that would give you the value of the definite integral. Unfortunately, we can't do that because we're not able to find an antiderivative of sine of x squared. So the next thing that we can think of is to approximate the value of this definite integral. And the way we will do that is by using a power series to represent the integrand. And then because each term from our power series is a power function, we can easily integrate power functions using the integration rule for power functions. So let's go ahead and do that. So we will begin by rewriting the integrand, representing the integrand sine of x squared with the power series. So again, you go to the power series for elementary functions, and here is the power series centered at 0 for sine of x. And to get the power series for the integrand, which is sine of x squared, you're just going to replace every single x in the power series for sine x with x squared. Just as a note, the integrand that we have for this problem is different from what we had for the very first problem that we did today. In the very first problem, we had sine squared x, which is, of course, sine of x squared, which is sine x times sine x. But that's not what we have in this problem. We have sine of x squared. It is the argument that is x squared. So just wanted to point that out. So for this problem, how do we deal with it? As I just said a minute ago, we're going to look at the power series for sine x and replace every single x with x squared. So that gives us, for the first term we'll have x squared, and for the second term we'll have minus x squared to the third would be x to the sixth over 3 factorial, plus x squared to the fifth will be x to the 10th over 5 factorial, minus x squared to the 7th will be x to the 14th over 7 factorial. And of course, there are infinitely many terms. Infinitely many terms. I can't write all of them, so I'll just write the ellipsis, showing that it continues. And in fact, if you wrote out all of the infinitely many terms, this would be exactly equal to our definite integral from the problem. But what we want is to approximate this definite integral. So basically, how do we do that? This is how we started, and I'll talk more about how we get an approximation and how we determine the accuracy of our approximation. So the next step in the process is to go ahead and use the fundamental theorem of calculus, which states that the definite integral can be evaluated by finding an antiderivative of the integrand and evaluating the antiderivative at the upper and lower limits of integration and subtracting. So we'll do exactly that using the fundamental theorem of calculus. So how do you find an antiderivative of x squared? It's a power function, so you add 1 to the exponent and you divide by the new exponent. And you do the same with the other terms. So you're going to add 1 to the exponent, so you get x to the 7th, and divide by the new exponent of 7. And you have the 3 factorial that was in the denominator to begin with. And you do the same thing with the remainder of the terms. So add 1 to the exponent, so you get x to the 11th over 11 times 5 factorial minus x to the, add 1 to the exponent, so you'll have x to the 15th over 15 times 7 factorial, and so on. And they are infinitely many terms. So you have an infinite series, which you need to evaluate at 1 and at 0, the upper and lower limits of integration, and subtract. Now, it turns out that when you evaluate each of these terms from the infinite series at 0, you would just get 0. So you don't really need to subtract anything because you'll just be subtracting 0. So you just really have to evaluate your antiderivative at the upper limit of integration. And when you do that, here's what you get. You substitute 1 for x, so regardless of what power x is raised to, you'll just have 1 in the numerator. So you have 1/3 for the first term minus 1 over 7 times 3 factorial for the second term plus 1 over 11 times 5 factorial for the third term. 11 times 5 factorial minus 1 over 15 times 7 factorial plus and so on. And let me just use red here to separate the two lines there. So take a look at what we have at the very bottom. That's an alternating series. You can see the alternation of signs. Does this alternating series converge? It does converge, and you can convince yourself that it converges by remembering the alternating series test. If you look at the terms, the limit of a sub n as n goes to infinity will be 0, because you can see that as we go into the series, as n increases, the denominators are getting larger and larger. So the limit of a sub n as n goes to infinity will be 0. And it is true that a sub n plus 1 will be less than or equal to a sub n for all n, because if you compare two consecutive terms, the next term has a larger denominator, so it will be smaller. So we have a convergent alternating series. And of course, it has infinitely many terms. But you may remember something called the Alternating Series Remainder Theorem, which allows us to approximate the sum of an alternating series, the infinite sum of an alternating series, by using a partial sum, and it tells us that the error of our approximation will be less than or equal to the first neglected term. So we can use that to help us with this problem. We can approximate this infinite series, the sum of this infinite series, and know the accuracy of our approximation by using the alternating series remainder theorem. So you saw on the previous screen how we went from our problem to this line, and I'm just omitting the steps in between so that I can have some space here. And as we just stated, we're going to approximate the value of this definite integral, which is exactly equal to the sum of this infinite alternating series. But we want to approximate the sum of the infinite alternating series by using a partial sum. And then we will use the alternating series remainder theorem to know the accuracy of our approximation. So we will, for example, use the sum of the first three terms. So we will approximate our infinite sum with the third partial sum, which would be what you see here. 11 times 5 factorial is 1,320. 7 times 3 factorial is 42. So what is that approximately equal to? That is approximately equal to, and again, this is approximating what? The definite integral from our problem is being approximated by the third partial sum of our alternating series, and that's approximately 0.3102. Now, how do I know that this is the accuracy that I want in this problem? So when we go back to the instructions, it states, use a power series to approximate the value of this definite integral with accuracy to 4 places after the decimal. So how do we know that we do have accuracy to 4 places after the decimal? We know because of the alternating series remainder theorem. It states if a convergent alternating series satisfies this condition, that's what we have here, then the absolute value of the remainder involved in approximating the infinite sum which is exactly equal to our definite integral. If we want to approximate the infinite sum, or in other words, if we want to approximate the value of this definite integral by a partial sum of the infinite series, the alternating series remainder theorem tells us that the error of our approximation will be less than or equal to the first neglected term. And what is the first neglected term? Well, we added these three, so the first neglected term would be this one here. And what is the value of 1 divided by 15 times 7 factorial? So the first neglected term is 1 divided by 15 times 7 factorial, or 1 divided by 75,600. And if you wanted to write that as a decimal, it would be about 0.0000132, and so on. But the point is, the alternating series remainder theorem tells us that the error of our approximation will be no greater than this value. And basically, if you take a look at this value, we have 4 zeros after the decimal. So if you just add to our approximation the maximum error we could have, it would still be accurate to 4 places after the decimal. Or you can subtract the maximum error we could have, and it would still be accurate to 4 places after the decimal. You should really look at what you have for the digit after the 2. And I did consider that, and it works out. So we just looked at an example for objective 3. You'll be able to approximate the value of a definite integral by representing the integrand with the power series and then applying the fundamental theorem of calculus. So generally, our 3 examples for today's objectives went over applications of Taylor series to help us solve other math problems.